Hey guys, we're starting chapter 15 in 1212. This is usually the first chapter that we cover for test 3. Equilibrium is the lead-in topic for chapter 16, which is acid-base chemistry. A lot of things we learn in this chapter will be fundamental when we get into the next couple of chapters. So make sure we learn this chapter really well. It's not one of the harder chapters, but we introduce the idea of reversible reactions. In chemistry, most reactions that happen actually are reversible, meaning when we mix the reactants together, they can react to form the products, but a lot of times the products can actually react and turn back into the reactants in some cases. As I said, most reactions are reversible, although not all are. In most chemical reactions, we're going to tell you whether they're reversible or not, but there are cases where that's something that we can easily predict. So, for example, if we talk about taking a piece of ice and melting it to form water, that is a reversible process. Now, that's not a chemical reaction, that's a physical change, but we can melt ice to make liquid water. We can also take liquid water and freeze it to form ice. Okay, so that process can go either way. So we could call that a reversible process. Similarly, we can take a gaseous sample and we can take all the air in the room and we can compress it down into a smaller tank. But then if we open the tank up, we can allow the gas to expand back out into the full volume it was before. So again, the compression or expansion of a gas is a reversible process. But then the next one, chopping down a tree. Once I chop down a tree, there is no way to effectively put the tree back the way it was before I chopped it down. I mean, I can stand it back up, but once you've cut through it, you can't fix that, right? So not every process is reversible. Similarly, if I burn a piece of wood, there's no way to undo that reaction. Combustion reactions are irreversible. I mean, there are ways of getting the components back into the same form, but it's not a simple reversal of the original process. There's a much more complicated way that would have to happen. But what about the carbonation with soda? If you open up a soda, all the CO2 will escape from the solution and the soda goes flat. Typically, a lot of students think that the carbonation of soda, once it goes flat, that would be an irreversible process, but that's not true. If you take dry ice, which is solid CO2, and drop it down into a liquid, it will release CO2 into the solution and it will recarbonate the liquid. Also, you could take CO2 under high pressure, force it into a container with the liquid, and then close the lid. At that point, some of the CO2 is going to redissolve, right? So there are several easy ways to recarbonate a solution even after the CO2 has escaped. So specifically, there's an example that kind of helps students understand the idea of equilibrium in terms of a chemical reaction. We call it the two balloon experiment, where essentially I have two balloons connected by a valve. Initially, if we pretend all the gas in the balloon is on one side, so let's assume the blue balloon is full of gas, and then the yellow balloon is empty, so pretend there's no air in there. If I open the valve and I ask what happens, most students will say the air from the blue balloon will travel through the valve into the yellow balloon. So then we talk about it further and say, okay, well, will all the gas pass through the valve? And the answer is not really. Students say it'll end up where half the gas goes through and fills out the yellow balloon. The blue balloon cuts down to half the size. And again, most students assume that the two balloons are going to end up with equal size, where half the gas stays on one side and half the gas stays on the other side. Okay? Now, we can expand on that to say, if I allow the gas to pass through, I get to half the gas on each side. If I close the valve, that creates a situation that we call static equilibrium, meaning it got to a balance point and then we stopped any movement between the two balloons because the valve is closed. Okay? With chemical reactions, that is not what usually happens. we have to imagine we allow the gas to go through. I get the two balloons to be about equal size, and if we leave the valve open, what actually happens is there's still going to be gas going from the blue balloon through the valve to the yellow balloon, but there's also going to be gas going from the yellow balloon back through the valve to the blue balloon. So even though the balloons are going to maintain about the same size, half and half, there's still going to be gas moving back and forth between them. It's just that the rate that gas moves from left to right and the rate that the gas moves from right to left, they're going to cancel each other out and still create a balance point, but this is what we call dynamic equilibrium. There's still movement back and forth between both sides. They're just balancing each other. Okay? In chemical reactions, this is the scenario that we talk about, where we have a chemical reaction where it starts out, we have reactants. As they react, we're going to form some products. But initially, we're only going to have the forward reaction going on. The reactants are becoming products. But then as we form products, some of those are going to start to react and go back to the reactant side. The forward reaction is the only one that happens at first, and it happens fast. The reverse reaction initially doesn't happen at all, because if there's nothing on the product side, there's no reaction that can happen to go back. But as I form more products, then I have the potential for that reaction to go back faster and faster. So the forward reaction starts out fast and slows down over time. The reverse reaction starts out zero or very slow, and it speeds up over time. And essentially, if the forward reaction rate comes down, the reverse reaction rate goes up. They're going to meet in the middle. And at the point where the rate of the forward reaction and the rate of the reverse reaction are equal to each other, that's where we're going to establish the balance point, which is what we call equilibrium. Okay? Now, next thing, if we talk about the size of the balloons, I said earlier that we generally assume that when we open the valve, the amount of gas that goes through the valve is going to set it up so that the two balloons will be equal size. That's actually only true if the two balloons are identical to each other. Now, in reality, no two balloons are going to be perfectly identical. Some balloons are a little bit more stretchy or elastic than others. You have balloons that are made of different materials. So there are a lot of factors that could come into play where we might actually have one balloon that ends up being bigger than the other balloon, even when it reaches equilibrium. Okay, it's not always going to be a 50-50 ratio once it reaches that balance point. Realistically, with chemistry, when we allow a reaction where the reactants form products, the products can go back to form reactants, when it reaches that balance point, the ratio of the products and the reactants is never going to end up being 50-50. Just realistically, it's never going to happen, because that ratio is going to be based on what we call the thermodynamic stability of the molecules. If the molecules on one side are more thermodynamically stable, which essentially means that their energy is lower, then more of the molecules are going to be on that side than the side that is less stable, which means they'll have higher energy. We don't want to have molecules that are higher in energy. So the ratio of products to reactants is going to be based on which side's more stable than the other. All right? So that's going to be important when we start getting into equilibrium constants, and that's going to be the ratio of products to reactants. So remember that fact when we get to there. So when we write equilibrium reactions, there are specific ways we write these. So again, we mentioned the freezing and melting of water. So if I have solid water, I can write a reaction. Now this is technically a physical change instead of a chemical reaction, but we can still write it this way. Solid water can be converted into liquid water. That's the melting of ice. But I can also write a reaction for the freezing of liquid water. The liquid water turns into solid water. Okay? Well, instead of writing these as two separate processes, we can combine them to show that it's a reversible process, and we can write one reaction that involves a double arrow. Solid water can react to form liquid water. The forward arrow on top says it can go from left to right, but then also the liquid water can be converted back into the solid, going from right to left. Okay? Both are possible, which is what this double arrow is trying to tell me. Similarly, now we look at a real chemical reaction. We can have the molecule N2O4, dinitrogen tetroxide. It can react to form two NO2 molecules, so that would be a decomposition type reaction. But then we can also have combination where two of these NO2 molecules can combine to form N2O4. Those reactions are exactly the same, they're just opposite, moving different directions. So we can combine them with a double arrow to say that N2O4 can decompose into this, or these can combine back into N2O4. Now, that actual reaction, it is a real reaction where I can take solid N2O4. If I warm it up, as it turns to gas, that allows the molecules to crash into each other and the reaction starts happening. So as the reaction starts to happen, what we know, again, chemically, N2O4 is a colorless gas. Okay? As it reacts, NO2 is a brown gas. It's a dark brown gas if it's very concentrated. Okay? Now, we start out where all we have is N2O4, that's our reactant. As it turns into a gas, and it goes straight from solid to gas, it sublimates. So as it turns into a gas, the N2O4 molecules start reacting to form NO2. I notice that because I start to form a brown color in the container. Okay? And then give it time, the brown color becomes more and more intense until it reaches a point where it kind of levels out. Now, if we analyze that container, it does still contain some N2O4 and some NO2. It'll be a mixture of the two because the forward and reverse reaction are both happening. So I'm going to eventually stabilize at some ratio of N2O4 to NO2 that's stable, and it'll stay at that ratio forever. So once it reaches a certain level of brown color, it's going to stay at that color forever unless I mess with it somehow, which again is the later topic for us to talk about. So, in a graph, if we take a solid piece of N2O4 from the previous slide, so my initial amount of N2O4 is a high number, but then there's the amount of NO2 initially is 0. As the solid sublimates, I'm going to form N2O4 gas, but then that starts to react. The amount of N2O4 is going to go down. The amount of NO2 is going to go up. Just like we learned in chapter 14, as a reaction progresses, it's going to slow down. But what we notice is, like the N2O4, as the reaction slows down, N2O4 does not approach 0. I'm never going to fully use up my reactant. Okay? I'm also not going to be able to make the maximum amount of my product, the NO2. It never really reaches the maximum amount that it could reach because of that reverse reaction that the forward reaction can go to a certain point, but then when the reverse reaction speeds up, it's going to reach that balance point where it's just going to maintain whatever ratio we have. It's going to maintain that ratio forever. Okay? Now, in the second graph on the right, and it's not showing up very well in the video, but hopefully you have the PowerPoint. This graph shows the rates of the two reactions. Initially, all we have is reactants. We have the maximum amount of reactants, so that's going to be the point where the initial rate of the forward reaction is going to be the fastest it can be. So the rate of the forward reaction starts out high. Over time, the amount of reactants is going to decrease, so that forward reaction is going to slow down. The reverse reaction starts out with 0, meaning the rate of the reverse reaction, it can't happen at first because I don't have any products. But as I form some products, then that reverse reaction can start going. So as the forward reaction happens, form some products, then that's going to allow the reverse reaction to get faster and faster. These two rates, the forward reaction and reverse reaction, they're both, the forward reaction is going to slow down, the reverse reaction is going to speed up until they reach the same level. And at the point where I can say, okay, the forward and reverse reaction are moving the same speed, At that point, that's when equilibrium is established. And if you look, both the forward and reverse reaction, their rates are going to stay together forever. As long as I leave that container sitting there and I don't disturb it, both reactions will keep happening, and they happen at exactly the same rate. So I will maintain the same amount of products and reactants in the container forever, even though I'm still making new molecules on both sides, but they always will balance each other. Okay, so again, all those things I just said. So we have another reaction. I will say throughout the PowerPoint there are places where the double arrow symbol gets messed up. So like right now in my PowerPoint, I came to a new classroom and this classroom doesn't have the latest update. So the double arrow in between, there should be nitrogen molecules react with 3 hydrogen molecules to form 2 ammonia molecules. So it's a 1:3:2 ratio. It is an equilibrium process where the nitrogen and hydrogen can combine to make ammonia, or the ammonia can decompose back to nitrogen and hydrogen. Looking at the graph, we can see that it doesn't matter what I start with. I will always reach equilibrium for this reaction in the same way. Now, what does that mean? Well, the graph on the left, I'm specifically starting with, I have a container. I put in a 3-to-1 ratio of hydrogen and nitrogen. So I'm starting with the pressure of nitrogen and hydrogen is a 3-to-1 ratio. I start out with no ammonia. Okay? So I only have my reactants on the left side. I don't have any of the products on the right side. As it reacts, the concentration of the nitrogen and hydrogen go down, the concentration of ammonia goes up. None of them go to 0, but they get to a point where a certain pressure of each one is established, and it will maintain those pressures forever. Now, that assumes I started with reactants and no products. The second graph, I've done the opposite. I take a container and I just put in ammonia. NH3 is my product. I just put in ammonia, and what happens then, my reverse reaction takes over. The ammonia is going to decompose back into the nitrogen and hydrogen, and when it does that, my ammonia concentration now comes down. My nitrogen and hydrogen concentrations go up. Again, they go up in their 3-to-1 ratio based on the chemical reaction. But if you notice, the ratio of the 3 compounds in this experiment end up being exactly the same as the ratios that have in this experiment. So what that shows me is it doesn't matter whether I start with reactants or products, doesn't even matter how much of each one I start with. If I allow this reaction to get to equilibrium, it'll always end up giving me the same ratio of products and reactants, because if you remember what I said, the stable ratio is based on the thermodynamic stability of all the molecules. And it doesn't matter how much you start with, it's always, the reaction always wants to get to that preferred ratio, because that's where the forward and reverse reactions are going to cancel each other out. So no matter what starting composition of reactants and products, no matter what I set up, once it reaches equilibrium, it's going to establish the same ratio of the products to the reactants. So now that we're going to bring back a little bit of stuff from chapter 14 and apply it to develop a new value called the equilibrium constant. So if we remember from chapter 14 how to write a rate law, the rate equals K times the concentration of the reactants raised to the order, and if we are dealing with a elementary reaction, which most of the time we're going to assume for this section that we do have an elementary reaction, okay, the exponent for the order is going to match up with the coefficient from the reaction. So if I look at this reversible reaction, the forward rate law is going to be the rate equals Kf, that's the K of the forward reaction, times N2O4 to the first power, because I have one N2O4 molecule there. Okay, then I can also write the rate law for the reverse reaction. The reverse reaction, again, I'm starting on the right and going back to the left this time. There's 2 NO2 molecules here. So my rate law will be the rate equals Kr, which is the rate constant of the reverse reaction, times NO2 squared. Squared because of the 2 in the balanced equation. Now, when we reach equilibrium, I know that these two rates are supposed to be equal. So that's what we're going to do, is we're going to set the rates equal and then do a little bit of rearranging. So at equilibrium, we set the rate of the forward reaction equal to the rate of the reverse reaction. So that means I can take the two rate laws that we just wrote, I can set them equal to each other. And then at that point, I'm going to rearrange to put the concentrations of both the reactants and products, put all the concentrations on one side of the equation and all the K values on the other side. So when I do that, and here I basically divided the N2O4 underneath the NO2, so that gives me this side, and then the Kr under the Kf to give me this side. Okay, so that's my rearrangement that happened. And then finally, when I look at this, Kf and Kr are both constants. So if I divide one constant by another constant, it just gives me a new constant. Kf over Kr equals some new constant value that we're going to call the equilibrium constant. So Keq is the new constant. It's the ratio of the forward rate constant divided by the reverse rate constant. Now specifically, when we rearranged the two rate laws up here, we specifically chose to move the concentrations so that when we divide one concentration under the other, we wanted to have the product on top and the reactants on the bottom. Specifically, that's the way the equilibrium constant is always set up. I want the concentration of the products over the concentration of reactants equals Keq. Now, Keq is a constant. It's based on the rate constants that I have from the forward and reverse reactions, and we know that the rate constant is affected by temperature. So Keq, the equilibrium constant, is affected by temperature, just like the rate constants from the last chapter. Okay? And then the last thing, the equilibrium constant has no units. It's simply a ratio of the products to the reactants. So it's like a 3-to-1 ratio or whatever. So we're just going to give a numerical value for Keq. Don't use units. I think that's a good place to cut off the video. We'll pick it up again next time.